best way to learn how to do unit conversions and calculations for concentrations, these various lab calculations, is to actually practice them. And I think it can help to kind of see someone's thought process as they work through these. Let's talk about making a sodium chloride, so a table salt solution.
So just a couple of notes that there are multiple ways to do things, and this isn't necessarily like the best way or the only way. So if you do it a different way, that's totally fine. Maybe this will help you see a different way that you could do it. Maybe you find something that's even better than I know. The basic idea, though, is that you should be able to kind of get comfortable working with numbers, working with conversions, do reasonableness checks throughout the way to see, do my numbers make sense? If things don't make sense, then look and see what you're doing wrong. I'm going to go over some ways that like I reason through things, some mental math and simplifications. Those can be helpful, but if you're just beginning out, it might be confusing. So feel free to skip those. And I've also included the more formal versions with dimensional analysis tables and things, which I still use dimensional analysis tables all the time. I just take some shortcuts along the way, moving decimals when doing metrics, units, and that sort of thing. So this first example is going to be preparing a 5 molar sodium chloride stock solution, which is something that I did just the other day. So say you are in the lab and it's your task to prepare 500 milliliters of a 5 molar sodium chloride solution. Okay, so how are we going to go about this? Our strategy. First, we're going to look up the formula weight for sodium chloride. And so remember that the formula weight, sometimes referred to as the molecular weight, but in this case, it's technically a formula weight because we'll get more into that later. But these terms are typically used interchangeably. Molecular is technically just a covalently bound complex, and we have an ionically bound complex, but anyway. So that formula weight or the molecular weight is going to tell you how much in grams a single mole weighs. And so I'm going to be talking a lot about moles. We talk a lot about moles in biochemistry. A mole is just like the biochemist dozen. It means 6 times 10 to the 23rd copies. So a big, big, big number, but we're working with really tiny molecules, so we can stuff a lot of little tiny things into a volume. And so then we can talk about moles per liter and as molarity. So this is the main unit of concentration that we use when dealing with biochemical molecules, but there are others. And in a later example, my next plan is to do one on sucrose solutions where we're preparing a weight volume percentage solution. But for now, let's stick to molarity, which is moles of solute per liter of solution. Where, as you can see, by 6 times 10 to the 23rd, we're going to be dealing a lot with scientific notation, this 10 to the notation. If you are not comfortable with scientific notation, I did a post on it just yesterday. The basic idea is that you want to be comfortable with the shortcuts where you can move your decimal places. When you're dividing by unit of 10, factor of 10, you can move your decimal place to the left. When you're multiplying by a factor of 10, you can move your decimal place to the right. And so, for example, when you're going between half a liter and or 500 milliliters, you can see that if you move your decimal place 3 to the right, because between a milliliter and the base unit between a milliliter and a liter, there's a 1,000-fold difference. So you can move your decimal place 3 places to the left from milliliters, or 3 places to the right from liters in order to convert between them. And so much more on that in yesterday's post, but it's something that you should get familiar with. And you're often moving by these factors of 3 because we're dealing with these metric prefixes that are separated by factors of 3. So a milliliter, that's 1,000th of a microliter, or a milli, that's 1,000th of a micro, that's millionth of a nano, that's billionth of a. These are the 3 that we use the most commonly in biochemistry, and you can see that they're separated by factors of 1,000. So we're often moving our decimal place by the 3s. And as I'll get into, sometimes it's easier to kind of do these conversions informally. So recognize that 500 mils is the same as 0.5 liters, so that we can work with these base units like liters, because molarity, moles per liter, that's going to be in terms of liters. So if our number is in terms of milliliters, we're going to have to convert. And sometimes it's easier just to do this into your head, though you can still do it in dimensional analysis. And so dimensional analysis is this other key concept that we're going to be using a lot. It's basically this idea that you can represent the same thing in a lot of different ways and convert. So you can represent a pizza, or you can represent a pizza as a certain number of slices that are in that pizza. And if you multiply something by 1, you don't change the number. So we can change units by multiplying by things that equal 1, but that let us change our units. And so with dimensional analysis, we line the things up so that our units cancel out. So typically start by taking like the main equation that you would use to get something, and then rearranging it for what I want to find, and then filling in unknowns with other versions, so with other equations and that sort of thing, replacing what I know, rearranging things with the dimensional analysis so that the units cancel out. And so say, starting from knowing that a molecular weight stands for grams per mole, and knowing that molarity is moles per liter, we can arrange these in different ways to solve for different factors, and then we can combine these equations as appropriate, making the units cancel out. So what do we want to know first? And so first of all, I just want to say more at the end, but I actually have these like cheat sheets on my, I have a Google Drive where I put some resources and I'll link to. But first we want to deal with this. What do we want to find? We said we want to prepare a 5 molar sodium chloride stock solution. And so 5 molar, that's telling us we want 5 moles per liter. And we need to figure out how much of that, we know how many moles, grams per mole, we found that molecular weight or that formula weight. And now we want to figure out how much of it we actually need in order to make 500 mils of a 5 molar solution. So if we go back to those ways that we could rearrange things, we could rearrange for mass to work out that it's equal to the molarity times the molecular weight times the volume. And these are all things that we know, so we can calculate this mass. We know the molecular weight because we just looked that up. That's the formula weight. We know the volume and the molarity because those are told to us. And so now we can just plug in the values and do the calculation. Here you can see that I've changed our volume from 500 mils to 0.5 liters using that shortcut where you can just convert with either just recognizing that it's that a 500 is 1,000, half of 1,000, so it would be half a liter, or shifting your decimal place 3 places because that's how the metric conversion and the scientific notation works. And you can also spell this out all formally in your table. And again, sometimes I would just go straight to putting the 0.5 liters in here instead of doing it like this and actually writing it out. But it can be really helpful to write things out, especially when you're unsure whether you're supposed to be multiplying or dividing. An easy thing to help with that too is to try to think logically about it. So it can get easy to get lost in all of these numbers. But along the way, you want to be kind of like doing sanity checks, reasonableness checks to make sure that your numbers are getting bigger if they're supposed to be getting bigger, and getting smaller if they're supposed to be getting smaller. So we want to go from a milliliters in terms of milliliters to in terms of liters. So this is kind of like going in terms of pizza slices to in terms of pizzas. So we are going to, we want to think about the same amount of stuff, but in terms of larger units. And so our number is going to get smaller. And so we're going to be dividing by 1,000. And that's why we shifted our decimal place to the left. Okay, so how many moles of sodium chloride are in your bottle? So we've been thinking in terms of moles per liter, but how many moles? Well, there are a couple ways to do this. The simplest way is that since the definition of molarity is moles per liter, we can just rearrange this to see that the number of moles is going to be the molarity times the number of liters, which we just decided was 0.5 liters. So remember, you need to be in liters. so that you can cancel out with your liters in your molarity. So sometimes, even though we can write molarity, if we know it means moles per liter, it can be helpful to actually write out moles per liter so that you know what you need to cancel out. So we need to cancel out those liters, which is why we needed to convert our value to liters. And we could do this all formally with our dimensional analysis table. An alternative method, since we know how much we weighed out in this case, you can just divide that weight by the formula weight. So remember, the formula weight is going to tell us grams per mole. And so we can divide the number of moles is going to be the mass divided by the molecular weight. And so the mass needs to be in grams. In this case, our mass is in grams. And then the molecular weight is going to be in grams per mole. Because we're dividing by it, we flip this over and you can see that our grams are going to cancel out and we get 2.5 moles. Okay, but how many moles of sodium ions do we have and how many moles of chloride ions do we have? So sodium chloride is an electrolyte. This means that when it dissolves, it doesn't just dissolve, it also dissociates, so it splits into its component ions. So when you dissolve sodium chloride, it's actually splitting up into sodium and chloride ions. But when you measured out the sodium chloride, the formula unit, so the thing that the formula weight was calculated for, was for the entire sodium chloride. So that means that that weight per unit took into account the sodium and the chloride, but when you dissolve it, then it dissociates, the sodium and the chloride come apart. Now that weight the weight was still representative of the sodium and the chloride. So the only thing that changes is how many particles you have in the solution. So you end up with twice as many particles in the solution as you put in. This is represented by this term called the Van 't Hoff factor, or I. So you don't really need to worry about that term, Van 't Hoff factor, unless your teacher makes you or something. But the crucial concept is that you're getting twice as many molecules as you put in. So if we calculated that we had 2.5 moles of sodium chloride in that bottle, well, that means we have 2.5 moles of sodium ions and 2.5 moles of chloride ions. So how many combined moles do we have? Well, we have 2.5 plus 2.5 is going to be 5 moles of solute particles. Okay, so why do we care? Why does this matter? Well, it matters because when we're thinking about colligative properties, these depend on the number of dissolved particles. So colligative properties include things like boiling point elevation and freezing point depression. And when you have an electrolyte like sodium chloride, as opposed to a non-electrolyte like sucrose that doesn't come apart, well, here you're going to get more molecules than you put in, more particles than you put in. And so you're going to boost the amount of dissolved stuff, which means that you're going to have more of an effect on those colligative properties, such as freezing point depression, which is why we salt our streets instead of sugar them. Okay, I'm going to switch to the Word document version of this now because it's going to be easier to work with for this. But so we're on this part where we're going to talk about how many moles of sodium chloride per milliliter. So now we're going back to talking in terms of sodium chloride. So we're talking about 2.5 molar solution. So first, think intuitively. Should your number get bigger or smaller? We're going back to our pizza box thing here. So just like there are fewer slices in a single pizza than there are slices in a carrier bag full of pizza boxes, there are fewer molecules in a milliliter than there are in a liter. So how much fewer? Well, remember, milli stands for 1,000, which we can also write as 1 times 10 to the negative 3. So we need to divide the molarity by 1,000. Okay, so now actually do that math. And remember, the easiest way is just to simply move that decimal place 3 places to the left, adding zeros as needed to get 0.005 moles per mil. And we can also write that out formally with our dimensional analysis. Okay, we don't really like working with decimals and zeros and all of this stuff, and so we often work in terms of scientific notation. So how would we write this in scientific notation? So it would be 5 times 10 to the negative 3, or in the caret notation, 5 times 10 caret minus 3, which is easier for our computers to deal with and for us to type. An even simpler version, as long as you know what it stands for, is E notation. And so we could write this using E notation as 5e minus 3, where E stands for 10 to the. So remember, this E is taking into account that 10. So this is not, you would not write 5 times 10 to 10e3 or -3. You would write 5e minus 3. And you'll see this a lot, maybe in like calculators or in Excel, things like that. Okay, so that was moles per, what was that? Moles per milliliter. Let's talk about moles per microliter. So what is a microliter? Remember, a microliter is a millionth of a liter. So it's 1 times 10 to the minus 6. When we have a milli, that's a thousandth, and so a million divided by 1,000 is 1,000. So basically, there's a 1,000-fold difference between a milliliter and a microliter. And so if we can start by going from the base unit, from going from a liter, or we can start by going from a milliliter since we calculated milliliter. So let's start from the liter. So we can start there because, well, if you hadn't already calculated the milliliter, well, then this would be easier. So we have a millionth, which we can also write as 1 times 10 to the minus 6. And so we need to divide by a million instead of 1,000, but we do the exact same thing. And again, you could have done it starting from the milliliter. Okay, so again, we have a lot of zeros. And I'm not even going to try to like write that out, but when you have something like this, it gets tricky keeping track of all of those zeros. So we typically use scientific notation for doing and reporting the calculations. So we could say 5 moles per liter divided by 10 to the 6th equals 5 times 10 to the minus 6 moles per liter, because in terms of scientific notation and this exponents, when you have a minus, that means you're dividing. And so we can write this. This would be our scientific notation. And we could also write it as, instead of dividing by that, we'd be multiplying it by 10 to the minus 6. We could go directly to that. Either way, we're getting the same answer. And in E notation, we would do 5e minus 6. So we often, if we had this like minus 6, we would want to use a metric, just change it to a metric prefix that avoids having to use scientific notation at all. So since we talked about micro as meaning millionth, and so micro is mu symbol, often you see it abbreviated with just like a U because that's easier to type. I actually have it shortcutted into my keyboard so I can just like switch my keyboard to Greek and put the letter in, but you can also do Alt 230 if you don't use it that frequently. But this mu symbol basically means 1 times 10 to the minus 6. And so if we write it in terms of 10 to the minus 6, well, then this is going to replace this. And so we get 5 micromolar per microliter. And in the case of per mil, we had, so in the case of per mil, we had 5 times 10 to the minus 3rd moles per milliliter. And then we could rewrite that as 5 millimole per milliliter, because this 10 to the minus 3, well, that's the prefix that we use when we're talking, that's the metric prefix or the metric conversion we use when we're talking in terms of milli. Do you see something? Do you spot a shortcut? So in each of these cases, we're dividing both parts of the unit, so the mole and the liter, by the same metric conversion factor. So we're making them millimole and milliliter and micromole and microliter, so they both still have the same prefix. So if we start in terms of moles per liter, that volume will also be millimolar per milliliter, micromolar per microliter, nanomole per nanoliter, etc. It's those ratios that matter, and they stay the same if we add the same prefix. And so this is also true if they're different to start out with, but then you have a different conversion each time, but each of them will be like 1 step down. So if you started with millimole per liter and you divided those both by 1,000, you would get micromole per milliliter, and etc. So be aware of those shortcuts. And in a later post, I will do an example with a sucrose stock solution. But I think that this is enough for today because I need to format the rest of it and my computer wanted to crash. But I hope that this was helpful, and best of luck with your calculations. There are various like online calculators that you can use. I've actually been spending my the last couple of weeks, some of the weekends, learning Python by writing code that will do these calculations for me, and I've been using them to check my math. But you should only use these once you actually know how they work. And so although I sometimes take shortcuts and use online calculators and code to make sure that I'm doing everything correctly, a lot of times at the bench, you don't have like a computer handy. And so you're actually jotting down these like dimensional analysis tables on paper towels and your gloves and stuff, but make sure you transfer them to your notebook. The basic idea is you need to know how to do these. And then once you know how, then you can use these sorts of tools to make your life easier. But remember these mental shortcuts too, like the reasonableness tests, checks to make sure that the answers that you're getting make sense. So it's easy when you have one of those black boxes where you're just putting numbers in to accidentally mess things up, not put in numbers correctly, not have be using the right tool and get an answer that is wrong. And so the good thing about doing it yourself is you can see where all these different components are coming from, and know why things are why. I will also post my own like cheat sheet type things. So advice for dealing with these metric prefixes, working with molecular weights and chemical concentrations. There's also some other resources here in this shared Google Drive. And so I'll post the link to that.